Welcome everybody. Today's lesson is on ionic compounds, specifically their solubility in water. And we're going to look at sodium chloride as an example. So first, let's take a look at a crystal of sodium chloride, which is table salt. And we have these little spheres. And here we have a green sphere that represents the chloride ion. And here's a purple sphere that represents the sodium ion. And notice there are many sodium chloride ions all attracted to each other and all in a big pile or crystal of salt. It is not just one sodium or one chloride, but many sodium and chloride ions all attracted to each other. Now here's another way to visualize this, where they're a little bit farther apart, but still we have the sodium, which is charged to positive, and chloride, which is charged negative. And so that's listed on this model here. Now, to tell why this is soluble in water, you have to know a little bit about water itself. So here is a visual of water, which is H2O. The red sphere is the oxygen. The white or bluish spheres are the hydrogen. And water is a covalent compound. It consists of just nonmetals, but oxygen is more electronegative, so it does not share the electrons equally with hydrogen. It pulls a little bit more and makes a partially positive side with the hydrogens and a partially negative side with the oxygen, because the oxygen pulls a little bit more on the electrons. So that side becomes a little negative and the other side becomes a little positive. Now that's going to be important to know why water can dissolve materials like salts or ionic compounds. So I found this little movie on YouTube and we're going to start it and look at what happens. So here is a little teaspoon of salt, and it's going to go in water and dissolve. But now we're going to look at it as if we could look at the microscopic level, or smaller even than the microscopic level. The waters surround the sodium, and then they surround the chloride. And notice they pull them apart, so they separate them. And it's the oxygen side that attracts the sodium, and it's the hydrogen side that attracts the chloride, because opposites attract. So the oxygen is partially negative, and sodium is partially positive. Sodium is positive, and the hydrogens are partially positive, and the chlorides are negative, and so they're attracted to each other, and the water can just pull them apart. So let's go ahead and watch that animation again, and you'll see it pull apart the sodium. First, the sodium is pulled apart by the oxygen side of water, and then the chloride is pulled apart by the hydrogen side of the water. And they get separated. So you have sodium surrounded by water molecules and chloride surrounded by water molecules. And that's why it looks like it disappears. So here's another animation with sodium and chloride. Here are different colors, but the largest one is the chloride and the smaller one is the sodium. And when you put this in water, you might see it as clumps at the beginning, but then it will look like it disappears. Why? Because once again, the water is going to break up this crystal with the hydrogen surrounding the chloride, and the oxygen side of the water surrounding the sodium, and will pull it apart. And that's why it gradually looks like it gets smaller and smaller pieces until it finally looks like it disappears, because individual sodium and chloride ions are too small to see with your eye. So there it is, disappearing, still there, just in very small particles. So now let's talk about the solubility of sugar instead of salt. Here is a sugar molecule. It is made of 12 carbons, 22 hydrogens, and 11 oxygens. Much larger than our water molecule. And here's two versions of it. Here is what they call a space-filling molecule, where the carbon is the gray area, the oxygen is the red, and the hydrogen is white. And here's another model of it. And this is not space filling. It's called ball and stick model, where you have the red is oxygen and the white is hydrogen, but this time the carbon is purple. Now, sugar is also a polar molecule because it has oxygen and hydrogen just like water does. And oxygen and hydrogen and carbon is a covalent molecule. And it does share, but it doesn't share equally because the oxygen pulls more in the electrons than the hydrogen because it has a high electronegativity. So just like in water, oxygen becomes partially negative and hydrogen becomes partially positive, but they still stick together because they are sharing electrons, which is different than an ionic compound. It doesn't share electrons, it transfers the electrons. And so when it dissolves, a little bit different happens. So what happens? Well, the water comes and it's attracting to the sucrose molecules, which is table sugar, but the sucrose stays as one big unit. Although when you have a spoonful of sugar, you have many, many sucrose molecules next to each other, attracted to each other. So when they dissolve, the sucrose molecules separate because the water is pulling them, but they separate as a unit from each other. So the sucrose still stays as C12H22O11, but they get separated from a big stack of them to individual sucrose molecules surrounded by water. So you can see this again in a PhET simulation, and we've done the PhET simulations before. So here we have some salt, and we can kind of shake it into our solution of water. And on the macro level, it looks like it just disappears. But about the micro level? What happens if I shake it? I have a whole bunch of sodium chlorides as crystals. Remember, the larger one is the chloride. But when it hits the water separates them. And we have individual sodium and chloride ions. And what happens if we do the same thing now with sucrose instead? What happens? I'm going to shake some sucrose molecules onto our... And notice the sucrose still stays attached. The carbons, the hydrogens, the oxygens still stay together as a unit of C12H22O11, but the individual sucrose molecules separate from each other. So a little different. Sodium chloride, the sodium and the chloride separate, but sucrose, the carbon and the hydrogen and the oxygen do not separate from each other. We can also look at this in water. So here's water molecules, and let's add some salt. What happens to the salt? The sodium and the chloride separate from each other. Now let's try it with the sugar. The sugar in, what happens? The sugar molecules do separate, but it does not break apart into individual carbon, hydrogen, and oxygen atoms. They still stay as a whole unit, but these units do become separated from each other. We'll talk more about this in class. Thanks for listening.